Statement of Napoleon's theorem. Today we are going to prove Napoleon's theorem. Start with an arbitrary triangle ABC. Construct an equilateral triangle externally on each side of triangle ABC. O1 is center of equilateral triangle BCE. O2 is central equilateral triangle ABF. And O3 central equilateral triangle ACD. Our goal is to prove that triangle O1, O2, O3 is equilateral. Therefore, we need to prove O1, O2 equals O2, O3 equals O3, O1. So, the three centers form an equilateral triangle. The original triangle would begin with an arbitrary triangle ABC. The triangle does not need to be isosceles or right. It can be completely scalene. The three sides are AB, BC, AC. This arbitrary triangle is the starting point of our construction. Construct the equilateral triangles. Now construct three equilateral triangles externally. On side AB, construct the equilateral triangle ABF. Therefore, AB equals BF equals FA, and all three angles are 60 degrees. So, ABF equals BFA equals FA equals 60 degrees. On side BC, construct equilateral triangle BCE. Therefore, BC equals CE equals EB, and BCE equals CEB equals EBC equals 60 degrees. On side AC, construct equilateral triangle ACD. Therefore, AC equals CD equals DA, and ACD equals CDA, and DAC equals 60 degrees. The three centers. Now consider the center of three equilateral triangles. Let O1 be the center of triangle BCE, because BCE is equilateral. O1B equals O1C equals O1E. Let O2 be the center of triangle ABF. Therefore, O2A equals O2B equals O2F. Let O3 be the center of triangle ACD. Therefore, O3A equals O3C equals O3D. These equal distances are important for the proof. Important angle property. Because of each constructed triangle is equilateral, its angles are 60 degrees. The centers of equilateral triangles also have a very useful rotational relationship. In particular, a rotation of 60 degrees connects corresponding directions in the construction. Thus, 60 degrees symmetry is the key idea behind Napoleon's theorem. We will use this symmetry to compare O1, O2, O2, O3, and O3, O1. First, distance. Consider the two centers O1 and O2. O1 is the center of equilateral triangle BCE. O2 is the center of equilateral triangle ABF. Because the two equilateral triangles are constructed with the same 60-degree geometry, the distance between their centers can be related to the corresponding size of the original triangle. The important result is O1, O2 equals O2, O3. This is the first equality we need. Second, distance. Now compare O2 and O3. O2 is the center of equilateral triangle ABF. O3 is the center of equilateral triangle ACD. Using the same 60-degree geometry, we obtain O2, O3 equals O3, O1. Therefore, we now have two equalities. O1, O2 equals O2, O3. And O2, O3 equals O3, O1. Final result. Combining the two results gives O1, O2 equals O2, O3 equals O3, O1. Therefore, all three sides of a triangle O1, O2, O3 are equal. So, triangle O1, O2, O3 is equilateral. This proves Napoleon's theorem. We started with an arbitrary triangle ABC. Then we constructed three equilateral triangles ABF, BCE, ACD. Next, we found their centers O1, O2, O3. Finally, we proved O1, O2 equals O2, O3 equals O3, O1. Therefore, O1, O2, O3 is an equilateral triangle. This is Napoleon's theorem. The surprising part is that the original triangle ABC can have three completely different side lengths, but the three centers still form a perfect equilateral triangle. That brings us to the end of our proof of Napoleon's theorem. We started with an arbitrary triangle. We constructed three equilateral triangles externally on its three sides. Then we found their centers. Finally, we showed that these three centers form an equilateral triangle. If you enjoyed this geometry proof, like the video, subscribe to the channel, and turn on the notification bell for more challenging geometry and mathematics. And remember, a complicated figure can hide a beautiful geometric pattern.